Okay, let's start. Do you have any questions? Okay, so just want to confirm that we do not have any day off, right, due to 4th of July. So all our classes are as normal, right? We're not going to have any class off, right, for 4th of July. So Monday, Wednesday, Friday this week, want to meet as usual. If there's any day off because of 4th of July that I'm not aware of, definitely please let me know, okay? But as far as I know, we're gonna just have classes as usual. Okay, so last time what we were doing was discussing, so we started chapter 2, right? Which is a big chapter about, basically random variables. So this is a big topic, right? But what we focused on last time was discrete random variable, right? So idea of discrete random variables. Okay. And basically these are random variables that take on discrete values like 1, 2, 3, etc. And so what are the things that we should know about discrete random variables? The first thing is, basically basic examples of discrete random variables. Um, so what? The Bernoulli, right? The binomial, the um, hypergeometric, sorry, the geometric, right? The um, negative binomial, let's say NP, um, and then the Poisson. All right. Now, of course, I mentioned last time that there would not be, it's not possible, right, to have an exhaustive list of basic examples, even if we, stick to the basic stuff, because, what does basic mean, right? And different people have different ideas of what a basic list of random variables include. And also, right, sorry, what else? Yeah. So, but anyway, right, so these are the ones that we will be seeing a lot, okay, in this class. And that's why you must know them by heart. So you must know basically their probability distribution function. Basically, you must know the probability that they take on some values for whatever, right, value that is non-zero. You must know their expectation to the extent that is reasonable. And actually, right, yeah, you should know expectation of all of the random variables. The variance, probably, right, as I said, um, you may forget, I mean, right now, this geometric, negative geometric, for example. But as we move along, this will be standard as well. So you should also memorize this. Okay. I mean, I do know that, right, on the exam, you have a formula sheet, and you can include this on the formula sheet. That's legal, but I mean, including this on the formula sheet means that, you have to leave space for some other things, as well as the fact that I am very sure that a student spending time looking up this information on the exam will not do well at all, because that basically they don't have not internalized, right, the basic models. Okay. Now, so these are the basic examples, but beyond this, right, the main idea or the key idea, let's say, key technique or whatever that is, that we covered last time, which will be repeated again and again in the prompts, right? In the homework and in your exam even, I'm gonna warn you ahead of time, is the fact, right, or the technique is to be able to express, right, a random variable as the sum or as a sum of, let's say, simpler, right, or more basic random variables. And so keyword here is sum, right? Summing random variables. Okay, I guess here, usually the sum, right? This is going to be IID, independent, identically distributed sum, okay? I guess doesn't have to, especially the word independent here. Well, you know what? Let me just skip that. Yeah. It's just sum, right? The reason why expressing a random variable as a sum of simpler random variables is helpful is because the simpler random variable can be, it's easier to compute, let's say, expectation and variance of these simpler random variables. Okay, and then you use linearity, right? For example, suppose you have a sum like this. Then by linearity of random expectation, you have this. Okay, and so basically, right, this is always true. You don't need any condition on the xi's. I mean, yeah, you don't need them to be independent of each other, whatever. So therefore, right, routinely even, to calculate expectation of random variable, in this class at least, you may want to, or you must ask, can I express it as a sum of other random variables? And very often than not, the xi may be, right, Bernoulli random variables. I'm saying maybe because it doesn't have to, depends on the problem. But a lot of times they are Bernoulli random variables, in which case they take on value 1 or 0, right? So in this case, they are indicator type of function. So you go through the category and you count, right? Whether or not item I, let's say, falls under the category or not. And so basically counting up using indicator function will be a very routine technique, okay, in this chapter at least. And mastering this technique, especially understanding or deciding which one, right, what is the right indicator function here will be, I guess, the key to either solve the problem successfully or not. At a similar level, the variance question proceeds along the same way, but variance, right, of a sum is a sum of variances plus the covariance. Let's do this, right? Twice the sum of the covariance. All right, like that. So the variance calculation, first of all, is more complex because you cannot just sum up the variance of the individual terms. You also have to calculate the covariance. But even with that, okay, this is still easier than to study the variance of the original random variable. So, okay, so basically, right, these formulas are stated, right, let's say in contrast to, as opposed to using definition. In other words, right, there's always a definition available. For example, expectation of x is sum over all range of values, right, times the probability that x takes on that such value, right? And the variance, can be stated simply as expectation of the square minus the square of the expectation, each of them following this kind of formula. But most of the time, right, even if you write down what the probability is here for, one of the non-basic random variables, computing this sum will be basically hopelessly out of the question. And the question in this class will not be given full credit or any credit, if you don't simplify the expression, if there's a simpler way, right, to simplify the expression. So this, I'll just tell you, no credit, not much credit. Usually, if you just write down a formula without any further elaboration, because anyone, right, can write this down without any kind of, meaning about, what they can do with this expression. Okay. So, well, case in point already, right? With this family, we already have the example of the Bernoulli, the binomial, right? As a sum of the Bernoulli, right? So if you sum up the Bernoulli random variables, then you get a binomial random variables, okay? As long as they're independent. And from this, we can conclude, right, that, so of course, a Bernoulli random variable has expectation as p, this is p times 1 minus p times 0, and has variance right, as expectation of the square, right? When you square a Bernoulli, the expectation stays the same because, it's just one square, right? And 0 squared goes p, and then minus p squared, which gives you p1 minus p, right? Well, but from here, right, then you have expectation of a binomial random variable, right? Clearly will be n times p, because it's, sum, right, n times, well, let me write it down, right? Like this. And each term here is p, right? So it's n times p. Now, in this case, we do have an independent sum, so we don't have to have the covariance term, right, in this particular example. So the variance is sum, so that's np1 minus p, right? Another case, of course, is the sum like this, but now we have to have the geometric, right, random variable. If you sum up the geometric random variables independently, then you get a negative binomial, right? Of course, you also have to memorize the meaning of these random variables. geometric, right, is the number of trials until you see the first success. Negative binomial is the number of trials until you see the first n successes, right? Which explains why the sum works that way. And then again, right, expectation of a geometric random variable is 1 over p. The variance, right, is whatever. I think it's p 1 over p, 1 minus p, whatever, right? But let's just put, let's just put a sigma square here, right, as a placeholder. We will calculate this, okay, when the time comes. And then after that, we're going to memorize it. But whatever it is, and then expectation of x will be n over p, exactly following the same kind of calculation. And the variance of x is n sigma squared, right? Whatever this sigma squared is, for exactly the same calculation. Any question? Now, the most notable application, right, of this technique is the coupon problem, right? Which is something, I mean, there are many coupon problems, okay? So when I say a coupon problem, which one? And it's just because, right, what is a coupon problem? A coupon problem is basically any problem where you have a item that can be of so many types. All right. Whenever you have that kind of thing, you will have a coupon problem. And when you think about it, right, well, you can have a ball being of so many colors. You can have a literally a coupon, right, being of like different types, like type 1, type 2, type 3, etc. And the question can change, right, from problem to problem. So again, we'll do more problems, as you can see. But so the one that we did, right, last Friday was of this type, right? Basically, a coupon, right, can be any of R types, right? I forgot what the letter they use here, but there are types, let's say, right, independently. So basically, right, you collect coupon, right? And then let's say you have a collection of K coupons, right? Find the expectation of the number of different types, right, in the collection. All right. So once again, right, you can say there's type 1, type 2, etc., right, up to type R. Any coupon can be of this type. If you have a collection of K coupons, then let's say you can have first coupon being type 2, type 2, type 4, type 4, type 4, etc., right? And let's say, let's say K goes to 5. So, and then type R, right? So, OK equal to 6. In this case, right, this particular collection has 3 different types, right? But of course, it's random, right? Because you could have a different collection, and then all of these may be of different types, who knows? So it depends on how K and R, right, interact. But overall, right, we want the average number of this, right? Okay, I know that we have done this question before, but it's a very important question to, I don't know, right? Just keep going over and over again for yourself if you haven't mastered, right, this kind of question. So I'm going to give you this quiz again. See if you can do it yourself without looking up the solution. this time. All right. So these problems, right, always proceed along the line that you let X be the random variables indicating whatever you want. So let X be the random variables, right, indicating the number of different types, right? In the collection. And then most likely you try to break X down into the sum of all the random variables, most often indicate a function. The task is to decide what are you summing over and what these random variables are. So in this case, right, what are we summing over and what are these random variables? What are we summing over here? So we are summing over each type, right? We go through the type and see if that type is in the collection or not, right? And exactly that's kind of how this example works, right? You go through the collection and see is type 1 in the collection? The answer is no. Is type 2 in the collection? The answer is yes, so on and so forth. And then you get to, right, 3 is the end, at least for that particular collection. So you sum over the type where the xi will be 1 if type I is in the collection, 0 if not, right? And so expectation of x here is a sum 1 to r of expectation of xi. And now what is expectation of xi? So I guess there's a word equally somewhere, right, in the example that I haven't written down. So basically what that means is, right, a coupon can be, any of these types can equally likely to happen. There's no type that happens more common. Basically, there's no rare type. We'll do a problem, right? I think there's a problem in your homework, either last Friday or coming up this Monday, where the types can have different probability. There's some rare type, but it's just some modification of, this problem anyway. But if the types are equally likely, then what is the expectation of xi? Well, xi is 1 if type I is in the collection. What that means is, right, okay, or maybe let me say this, right? When you have an indicator function like this, then you see, right, that the expectation of an indicator function is exactly the probability that it takes value 1, right? A Bernoulli random variable or indicator function, its expectation is exactly the probability that it takes in value 1, or basically, right, the probability that whatever the event that it's indicating happens. So let's just write that down, right? But it's going to be equal to 1 if, right, type I is in the collection. Well, we need to elaborate, right? But what does that mean? That means that you go through the collection and you see that at least one card, right, one coupon is of type I, right? Because if there's no coupon of type I, then that type is not in the collection. So basically, okay, again, elaborating, when we're used to this, we don't have to write down this elaboration. We can just write down what the probability is, but you know, okay, like that. And so whenever we see the word at least, then it's 1, 2, 3, etc. Then most likely looking at the complement is easier, right? And so now this can be done by independence, right? So no coupon is of type I. That means all coupons must be of the other type. So, right, I mean, so basically, all coupon must be of type other than I, which happens with probability, right? R minus 1 over R raised to the k power, because they're key coupons in the collection. Okay, and this is a sum like this. All right, so that's the solution in the abstract. Any question about this?
Wait, where did you get the R minus 1 over R to the K?
So there's a type right there, right? So let's say all coupons must be so no coupon in the collection, right? So let's say it can be of type 1. That means it can be any types other than 1, right? So the probability of that happens, let's say for the first coupon is R minus 1 over R, right? Because there's R type, and then R minus 1 over R type, so on and so forth. And then these are independent, so you multiply it k times. That's raised to the k power. Does that make sense?
Yeah.
All right, any other question? And of course, right, because all these numbers are not dependent on R, you can simplify it to this. But yeah, say you simplify it down to this. Sorry, the k power is inside, not outside. Like that. Okay. All right. Like I said, there'll be many indicator functions coming up for the homework. So Well, let's go over a few problems that were assigned on Friday. So I guess the first one is not really about that, but it's about interpretation, right? And as you can see, this class is a lot about understanding um, what the formula says rather than memorizing the formula. I mean, well, you have to memorize, right? Expectation, variance, probability of basic random variables, etc. But as far as we're concerned, there's no memorizing, let's say, this formula. Because, I mean, if you have another problem, you can be guaranteed that this is not the answer anyway, right? But the technique will be the same. I mean, right, to that extent. Whatever the final answer is, it's not really the same. So, quiz 2, this is question number 24 in the textbook, which says that a random variable probability x equals to k is r plus k minus 1, choose r minus 1, p to the r, 1 minus p to the k, where k can take value from 1, 0, 1, etc. Right? So there's no upper limit to k. Choose a possible interpretation for x. In other words, right, what would x be a model of? And this is just basically reading this formula and try to understand what it's trying to tell you. All right, what's an interpretation for this random variable? Or what should the expression remind you of?
Um, I think it's almost like a binomial random variable where R, I guess, represents the successes and then K represents not
Okay, that's not a
successive
bad,
trials.
yeah, that's not a bad attempt, except that how is this different from a binomial random variable? What's a key difference in this description?
Well, x
Yeah,
is
well,
represented. We're trying to find x equals k, and we're subtracting the total amount of trials by 1. So is
well,
it the number?
no, I mean, that's not the crucial difference since you're mentioning the binomial. What, okay, tell me, right? Well, okay, what does this notation mean? K equal to 0, 1, dot, dot, dot. Assuming that there's no mistake made, right, in this notation, which there should not be. What does this mean? This means that x can take any values from 0, 1, all the way to, I don't know, 1,000,000. What's the key feature of a binomial random variable? So this is about the support, right, of a random variable, right, which is the first question you must ask when you see a random variable. When you see a random variable, you must ask what values it can take. So here, what value can a binomial random variable take? 0, 1, and then what? Is that it? It can go on forever? It must stop at n, right? Because a binomial random variable is the number of successes in n trials. So from that point of view, even though, yes, you kind of pick up some clue about it, right? This says that it cannot be of the binomial type. Also, right, what variable changes here? K or R? Or both? The meaning of this expression is R is fixed, right? I mean, it's not I mean, it will be given in the problem, but whatever that value is, we don't change it. When you look at a binomial random variable, right, you will have n choose k, p to the k, let's say, 1 minus p to n minus k. Both of these will move as k moves, right? So what should this be compared to? Not the binomial, but the negative binomial, right? Because the negative binomial is what, again? It's the number of trials until n successes and first successes, right? And so what's the probability of x equals to k for a negative binomial? And what values can k take? N plus 1, etc., right? There's no upper cap. But what's probable of x equals to k? So out of k trials, right? What do you know? The last one must be success, because that's how many trials you need, right, to get to so many successes. So last must be a success. Well, then that means that among the first k minus 1 trials, that's a subtract 1, right? There must be n minus 1 successes. Right? So therefore, it will be k minus 1, choose n minus 1. And then the probability of success is going to be p to the n because the n successes total. The probability of the failure is 1 minus p. And raised to k minus n. Because, right, that's the number of failures remaining. Okay. So this should be compared with a negative binomial. But then, right, what's the interpretation of this random variable, right? Is because clearly it's not, right, exactly a negative binomial. So what is it? What does it represent? So here, right, if you pay attention, notice that this is p to the r, right? And notice that r is fixed here in this expression. The same thing as n is fixed in this expression. Because as k changes, n won't change, because that's just the parameter, right, of the model. So basically, the r here is the n here. So you're still kind of dealing with n successes or r successes, right? So, well, let me just line up the notation. Let's say r successes, right? The number of trials until the first r successes. Like that. Okay. So r minus 1 successes. But as you will see now, right? Basically, the key difference is here. Instead of k minus 1, we got r plus k minus 1. Instead of k minus r, we had k, but k runs from 0, 1. Instead of k runs from r to r plus 1. So k, right, exactly is the value x take in both expression. So what does it mean? It represents the number of failures, right, until the first R successes in independent trials. With success probability, sorry, P. Okay. And that's why it starts counting instead of R plus 1, it starts counting from 0, 1, etc. Instead of K minus R, it's just K. Any question? Okay, let's continue. So this is question number 42, which I believe is on the exam. Oh, sorry, on your homework. So suppose that each coupon is you know, same as the other coupon problem, right? Independently and equally likely to be any of the M types. So instead of R, you use letter M, right? Find the expected number of coupons we need to collect before, let's say not before, but in order to have at least one of each type. Right, so this is probably what people will call a full collection, right? All right, so first of all, do we understand or do we have an example in mind, right, of what this is referring to? Because when you read the problem, you have no idea what scenario it refers to, then you won't be able to solve the problem, right? Do we understand what this problem refers to? So basically, right, unlike the other collect coupon problem, there's no fixed amount of coupons we are collecting, right? So basically, right, you just collect, and let's say the coupon comes out to be 2, 1, 3, etc., right? But then it may repeat itself, right? 1, 1, 1, then 3, right? Something like that. And you keep collecting until, let's say, you know, every letters, right, from 1 to M showed up. That's exactly, right, when you have a full collection. And clearly, right, I mean, I say M here as in type M, but you know, M can show up before, right? Who knows? But basically, you keep collecting until you have every type, and that's a random number, right? So you let X be, you know, the number of coupons needed, right? Or number of size, the size of the collection, right? Then let's see if we even follow this. What values can X take? What values can X take here? Can X be 0 or 1? What's the least value X can take? Well, clearly you need M, right? Coupons at least, so that they can be each of different type, right? To have a full collection. That's the luckiest scenario. But of course, right, you can have a repetition, so on and so forth, right? There's no limit to, there's no upper limit, right? To how many you need to collect before you have a full collection. Is that clear? And then you know the routine, right? Or the technique. The technique is you must break x into a sum of xi. And the task or the challenge is to decide what the xi's are, what should they represent, and what are we summing over. So X is the collection, the size of the collection, right? So what are we summing over? Well, so the textbook is more kind, I guess. They give you this hint, and they said xi is a geometric random variable. All right, so that's how much they give you. So they give you more than I asked, maybe, but you know, it's a homework problem, so you might have seen it before. So that there, but I guess of course the question is what kind of geometric random variable, and what does xi represent anyway? So what is this hint about? That x be this sum where each xi is a geometric what? What are we looking at? What should each xi represent? So what should we sum, right? So clearly M here is the M types, right? What should we sum across the type to get to the size of the collection? So clearly, right, xi represents the number of coupons needed until we see, right, type I in the collection. Does that make sense? And that's why it's a geometric random variable, because the success here is basically the number of coupons needed to see. I mean, well, there's something here that you need to be a little bit careful about. For example, but how does there's something we need to clarify here, right? For example, when you collect a coupon, right? The first coupon will definitely be of some type, right? So you will hit on some type right away. So let's say it's type 2. And then, right, you may have a 2 repeating until you see another type, let's say 3 or 4, whatever. So here the xi should represent number of coupons needed until we see a new type. A new type, right, of order I in the collection. You understand? So for example, right, what's x1? X1 is a number of coupons needed until we see a new first type. Well, how many coupons do we need to see a new first type? I mean, yeah, right. It'll be 1. It's not even a random variable because the first coupon in the collection, you will have a new type. But then, right, what's x2? What should x2 be? Once you have a type, how many coupons you need until you see a new type of order 2, meaning a second type? X2 is a geometric random variable, right? With what kind of success probability? M minus 1 over M. Right? Because once you have the first type, then it doesn't matter what that type is. Then you, right, say you have a 2, right? Then you wanna keep collecting until you see a coupon not of type 2, right? Once you have a 2, then you keep collecting until you see a first coupon not of type 2. That's a success, right? A failure would be to keep collecting 2, right? That's a failure after you get the first 2. Therefore, a success here, right, is to see a coupon not of type 2. That means the probability of success is M minus 1 over M, because all coupon types are equally likely. Okay, so far? Then what's x3? It's a geometric random variable with what kind of success probability? M minus 2 over M, right? Because after you get the first 2 types, let's say you hit on the 4, right? Then a failure would be to see these 2 repeating. And the success is to see another type, not of these 2 types. Let's say a 5. Okay, so far? So for example, right, in this sequence, this is x1, right? It's always 1. x2 is here. So it takes you 5 coupons to see a new type. And x3 is here. It takes you 6 coupons to see a new type of order 3. So on and so forth. We got it? And then of course, right, xm will be geometric of what kind of success rate? One over m, right? So with x being like this, what's expectation of x? So notice, right, this is an example where the xi's are not IID, right? I mean, yeah, I mean, well, so they're not identical, right? Are they independent? Well, I mean, when the coupons are equally likely, I guess they are independent because, right, our x2 takes value doesn't depend on x1, for example. But then they're clearly not identical because they have different success rate. Anyway, right, just to show you, or just to kind of point out that when you have a sum like this, they don't have to be even identical or independent, right? It's just a breakdown of the random variable into simpler, right, random variables we can control. But anyway, this will be, right, so is this, so it's going to be m over m minus I. I guess if we sum from 1 to m, then it's going to be m over m minus I plus 1. Like that. Any question? All right, let's continue. So this is question number 43 in your homework. An urn contains n plus m balls, of which n are red and m are black. They are withdrawn from the urn one at a time and without replacement. Let x be the number of red balls removed before the first black ball is chosen. Find expectation of x. Okay. So I guess, again, let's first try to understand the problem. And the key here is, do you have any idea what this problem is talking about? Because if you don't, right, then there's no hope of you solving the problem. So you should have some sort of like imagination, right, in your mind on what the problem is trying to tell you. So what should this from remind you of? Or what kind of random variable does X seem to remind you of? What flavor is X? What kind of random variable does X seem to be similar to?
I think hypergeometric.
Not really. If by hypergeometric you really mean hypergeometric, because hypergeometric, right, is to remove so many balls in the sample. So let's say you have blue and red, and you select R balls out of the sample, and you try to see how many blues and how many reds are in this in your subsample. Not hypergeometric. But and again, I guess here probably it's really up to you, it's subjective. Because here I would say it's more like a geometric. Okay, but I can see where the hypergeometric comes from. Why would I say it's similar to a geometric? Because it's really about keep performing something until the first success, right? That's the kind of the highlight of geometric. The geometric random variables keep performing something until the first success. And here, right, what is a success? A success is to see a black ball, right? You keep selecting ball out of the urn until you see the first black. That's a geometric. I mean, sorry, that's sort of like the taste, right? Keep doing something until the first success. But why would this not be a geometric random variable? And that's where, right, someone was saying it's a hypergeometric, right? Because it's without replacement, right? So in other words, as you keep drawing, right, the result of your draw affect the next draw, right? That's without replacement, what it does. I mean, imagine, right? In contrast, imagine if you withdraw and then you put the ball back into the urn. Then can you see that? So is that without, it's with replacement. Then can you see that it's exactly a geometric random variable? Right? So it's exactly, so that's why I say that the taste is more like a geometric random variable, except that it's a geometric where, I mean, again, right, I acknowledge that the use here is a little bit loose. This is not a geometric, but it's like that. So the key is you keep doing something until your first success, but the trials affect each other. Okay, that's why the problem here is, let's say, hard. This is not your traditional model. But anyway, right, we're concerned here with finding expectation. And so again, the taste is to break it down into individual term of simpler random variable we can handle. But I'm gonna let you guess here, right? The textbook tells you what it is, but on exam you will have to create this on your own. So I'll just might as well just let you see this, right? So what should the xi be? What are we summing over? Can you guess? So we want the number of red balls removed before the first black. So what can we sum up to get to that number? So again, right, the key here is to kind of see what X is a total of. For example, right here, X is a total number of coupons. So that's why you kind of break it down to sub, right, collection or whatever that is. Here, I guess here, right, X is a total number of red balls. So it may be a bit surprising if you don't do these problems a lot, but you basically sum over the red balls themselves. Sorry, N, right? N are red. So you sum up 1 to N, because N of them are red, right? And so what are you counting up? You count up whether basically you remove the ith ball before the black. Does it make sense? Because if the ith ball is the ith red ball, right? Not the ith ball, the ith red ball, right? I goes from 1 to N total red balls. Because if the ith red ball is removed for black, that counts as 1, right? You know what I mean, right? So for example, this is red 3, red 4, red 2, etc., right? And then there's a black. And then there's red. There's another black. We don't care. And then there's red 6, whatever, right? Then here, clearly, if you remove like this, then X equals to 3, right? Because there are 3 red balls removed before you see a black ball. Does that make sense? So, right, in this example, for example, X3 equals to 1, X4 equals to 1, X2 equals to 1, any other X, right, will be 0. Anyway, right, so that's how we break this down into smaller sum. The question is then, what is expectation of Xi? Because that's so to be clear, right? What does expectation of Xi represent? So notice, right, the Xi are Bernoulli random variables. And if they're Bernoulli, then the expectation is exactly equal to the probability is equal to 1. Which means what? It's exactly the probability that the ith red ball is removed before the first black. And the question is, what is that probability? What's the probability that the ith red ball is removed before the first black? Or the answer is it's 1 over m plus 1. Where what is m? M is the number of black balls. Do we see why? The reason, right, is because here, notice that here this probability is the same for all red balls. Because as far as a red ball is concerned, if you are looking at, right, the probability that it will be removed before black balls, then this probability is about the relative position between a red ball and the black balls. So it's not about the relative position of a red ball with another red ball, because it doesn't matter, right? If a red ball is removed before the red ball in question, it doesn't matter, because it's just doesn't count, right? So therefore, as far as any red ball is concerned, we're just really focusing on it relative to all the black balls. But as far as positioning goes, there's nothing special about the red balls and the black balls. In other words, right, a red ball can be in front of all the red. Let's say this is red ball number 2, right, that we're focusing on. Then it could be like this. In other words, right, it will be picked before all the blacks, or in any other kind of relative positioning, it will not be picked right before first black, because the first black will be picked before the red, right? And of course, in all these scenarios, right, how many balls are there? There are m plus 1 balls total, right? I mean, m for the black and 1 for the red, right? So the m plus 1 balls total, all of them are equally likely to take on any position. Therefore, the position that the red ball goes first is 1 over m plus 1. Any question? And so the final answer, yeah, go ahead.
Sorry, so it's not dependent on the number of red balls then?
No, that's the surprising fact here. That's correct. You should think of it very deeply. It doesn't. Again, right, I'll give you a hint, but that's all I can do. You have to think it out for yourself. The reason is comparing to the black is removed before the black, right? You think of it. If you have like 1 million red and 1 black, right? That's just kind of like make the situation a bit more exaggerated. Then what's the probability of any particular red ball being removed before black? Suppose you have 1 million red, 1 black, right? Suppose 1 million and 1 of you guys line up, and 1 million of you guys wear a red shirt, right? And 1 guy wear a black shirt. But randomly, what's the probability that you will be removed before the guy who wears a black shirt? But the key question is you, not just any red, right? You yourself. Because this is focusing on the ith red ball, you see. That's the whole point of sum. If you ask what's the probability of a red ball being removed before a black, yeah, that's a different probability. Does that make sense? But this is a particular red ball. And if you think about it, right, in this scenario, you see that if you're wearing a red shirt, then probably you being removed before the guy who wears the black shirt is exactly 1/2. Because there's half a chance you are lined up before him, and there's half a chance you line up after him. You agree? All right, any question? So right here, the expectation of x then, right? We being the sum, expectation of xi, and all of them being the same is n over m plus 1. Any question? All right. Move on. So this is question number 45 in your homework. It says that a total number of R keys are to be put one at a time into key boxes. So each key independently into box I with probability pi, right? So that's the experiment. So do we understand? So let's say you have 3 boxes, right? And you drop a key into each boxes with some probability. So they don't have to be equally likely, right? That's the whole point. But of course, right, here there are k boxes, so it goes without saying that what? The sum of pi, right? Where I runs from 1 to what is equal to 1? Is it R or K here? K, right? All right, so continue. Each time a key is put in a non-empty box, a collision occurs. So this is basically a definition of a term, right? So a collision is when you put a key into a non-empty box, right? So for example, you drop a key into the box for the first time, for that box, there's no collision. But later on, if you drop a key into the box again, there'll be one collision, right? But of course, if you drop another key, then there'll be another collision, right? So 2 collisions, so on and so forth. Are we clear? And of course, right, the question is, find the expected number of collisions. All right, that's the question. So the routine is, of course, if you let x be the number of collisions, then you want to break it down to simpler terms. Let's say x is a sum of, let's say, xi here. But what are we summing over? And how do we do it? What are we summing over? And what should each of the xi represent? So intuitively, right, it should be clear that you are, because you look at the number of collisions, and the collision kind of like is kind of box dependent, right? So say a box has 3 collisions, no collision, 2 collisions, and you have 5 collisions total. Then you want to sum over the boxes, where xi is the number of collisions in box R, right? Is that clear? So expectation of x would just be the sum of expectation of xi. Well, the question is, right, how do we find expectation of xi? What's the number of expectation, number of collisions in box I? So here you see, right, that basically, as far as a box I is concerned, then the number of collisions, right, is essentially suppose it has 3 keys in here, right? Then how many collisions do we have? 2 collisions, right? Because the first time a key is put inside the box, there's no collision. Then the second and third times, right, there is a collision each. In other words, it's almost like right, and you can make this into a random variable. Let's say a yi, right? Do you understand? So the number of keys, right, dropped into each box will be a random variable. And depending on how many keys in the box that is, right, subtract 1, you get a collision. So you get the total number of collisions, right? Except for one scenario, which is what? Except when you have no key in the box, right? Which is when yi equal to 0. Then you cannot subtract 1, right? Because subtract 1 means that you have minus 1 collision, which is weird. So if you have more than 1 collision, 1 or more collisions in the box, then subtract 1, you get the total number of collision. Does that make sense? For example, right, if you have 1 key in the box, then the number of collision is 0, because that's the only key in the box. But you can also have no key in the box, in which case you have no collision, because the box is empty anyway. So that's the only thing that I guess a little bit tricky about this problem. You have to kind of separate out the 2 scenarios. Are we clear on this? All right. So what values, right, then can xi take? Or what values can yi take? The number of keys in the box. So you can have no key in the box, or you can have, let's say, R key. Wait, is R already there? total R keys, right? So let's not say R. Can be K keys, right? Where K runs from 1 to R, right? So basically, I'm just separate out the scenarios, but you know, the number of keys in the box, right? Can be anything, any number really, right? From 0 to R. Is that okay? So what is this? What is this expression? What's the probability that we can get K keys into box I? Well, what kind of random variable is yi? Oh, you know what? I guess I reused the letter K, right? Because K is already used as a number of boxes. So let me use another letter, maybe N. So yi, right, is exactly a binomial random variable, right? Because why is it a binomial random variable? Because you go through each key and you say it's a success with probability pi, right? If it gets dropped into box I. As far as the box I is concerned, it's a success for a key to be dropped to box I, and it's a failure, right, if the key is not dropped into box I. So in other words, is R choose N, right? Among R keys, choose N keys to be put into box I. The rest must not be put into box I. Are we clear on this? All right. So that's probably why I equals to N. So notice, right? As far as we're concerned, if you are really looking at expectation of yi, then it's simple. Expectation y is going to be R times pi. This is a binomial random variable with R total number of successes, right? Sorry, R total number of trials. But we're not dealing with yi, we're dealing with xi. And xi is not exactly yi either. It's yi if y is bigger than or equal to 1, 0 y equal to 0. So, you know, let me see, right? Well, actually, what I'm trying to say is this, right? Hold on. Let me try to think. So expectation of, well, but what is expectation of yi, right? Expectation of yi is going to be the sum, right, from 0 to R, right, of this expression. So of n times R choose n, pi to the n, 1 minus pi to R minus n, right? Which is just n times probability y equals to n. But what I'm trying to point out to you is when n equals to 0, that even though this is a non-zero term, this is 0, so it won't contribute to the sum. So in fact, right, you can write it as sum from n equals to 1, like that, right? And this expression is equal to R times Pi, right? On the other hand, what is Xi? Xi is Yi minus 1 if Y is bigger than 1, and 0 if Y equal to 0. So in other words, right, Xi equals, right, the sum n equals to 1 to R of n minus 1, right, because it's Yi minus 1, times probability of Yi equals to n. Agree? And so it's going to be n equals 1 to R, n minus 1 times this. Okay. But if you distribute this inside the n minus 1, there'll be two terms, right? The first term is this sum, which is R times Pi. The second term is subtracting this. But what is subtracting this? This is the sum of all probabilities except the probability when Y equal to 0. So you can say it's subtracting 1 minus P0. Sorry, probability Y equal to 0 is not P0, right? Probability Y equal to 0 is every key goes to the other boxes, right? Like that. Are we okay? And so, right now, to return to X, then X will be just sum I from 1 to R of this. Like that. Are you okay? Any question? Or sorry, this is sum over the boxes, right? So I from 1 to K. All right, so I guess that's enough question for today. In terms of the homework, you have more questions of this type, okay, assigned for the homework for this week today. But let's continue with the lecture. So, well, what else can we say about, random variables in general? So we talked about discrete random variables, right? So let's move to the continuous family. So continuous random variables. So just like discrete random variables, right? With continuous random variables, you have to pay attention to the support, right, of the random variable. But maybe before that, right, let's take a step back and see, right, what is special about a continuous random variable. And what's special here is what? That a continuous random variable, the distinct feature, right, is that the probability that it takes on any particular value is going to be 0, right? Instead, what defines it, right, is the so-called density function, right? So this is the PDF. I mean, it's called the probability density function, right? or just the density. So basically, a continuous random variable is defined, right, by its density. All right. And so the support of a random variable, of a continuous random variable, is where the density is positive, right? Where it, because a density function must be non-negative, right? And so the support of a continuous random variable is basically, again, right, where the likelihood is non-zero. So that's the support. All right. So the task is the same. We want to list out the typical, right, continuous random variables that we will encounter. So basically, what are the random variables we should pay attention to on a continuous side? What is the support of such a random variable? What is the PDF? What is the expectation? What's the variance of those random variables? Again, right, the list is not meant to be exhaustive. There are random variables that are very important. Let's say the Cauchy, the beta, the gamma, right? These are very important random variables. The T distribution, for example, chi-square, they are all continuous random variables, but they are important for the statistics. They won't be really important. I mean, well, that's the wrong thing to say. We won't encounter them as much in this course. So when I say this, I guess I'm referring back to probability class, right? Where most likely you run over the more basic type rather than, let's say, the beta or gamma. But okay, so what's the most basic continuous random variable that you must know? Well, the most basic one will be uniform from A to B. All right, it's a uniform random variable. The support, of course, is from A to B, right? The interval. The PDF, because it's uniform, is 1 over B minus A. Expectation is B plus A over 2. Variance, B minus A squared over 12. Okay. What's the next one? The next one is exponential lambda. And most probably this one will be the most important one in this class if we ever get to the queuing model, because exponential is used, as the basic model for waiting time until some event happens. So exponential lambda, right, is the model for waiting time. So it's intimately connected to the Poisson random variable, because Poisson represents, right, the events, number of events that happen. Then the time it takes, right, they call inter-arrival time. will be exactly exponential if the model is called a Poisson arrival model. Anyway, what's the support for a Poisson? Oh, sorry, an exponential. The support is from 0 to infinity. Okay, it only takes non-negative values. What's a PDF? PDF is lambda e to minus lambda x, non-negative. Excitation, 1 over lambda. Variance, 1 over lambda squared. Okay. And truth to be told, these are probably the two that we will encounter the most in this course. There's actually the gamma, but this is even further down the road. And the reason why we care about gamma is that independent sum of an exponential gives you a gamma random variable. Okay. So basically, if you have inter-arrival times and you look at the total right time for, like, let's say 3 events to happen, that's a gamma random variable. Support 0 to infinity. PDF, let's say we skip for now because the PDF of a gamma is not something people are super interested in. But the mean is n over lambda. The variance is n over lambda square, which you can kind of guess where it comes from. Because if you sum up exponentials, independent exponentials, you get gamma. And that's why, right? So again, this is yet another pair, right? Like Bernoulli and binomial, geometric and negative binomial. Now you have exponential and gamma. The last one, right, to be mentioned is a normal. We won't encounter normal in this class at all, but we're just gonna list it there, just, you know, because, right, it's so important, the random variable. This guy will be important if we talk about the Brownian motion, which I doubt that we ever have time to go into. So we're just gonna leave it there. Support minus infinity to infinity. This is mu sigma square, so density will be square root 2 pi sigma square e to minus x minus mu squared over 2 sigma squared. Excitation is mu, variance is sigma squared. All right, any question? So again, right, these are random variables that you're supposed to be familiar with for a class. Well, for now, you know, unless the question is about just the random variables in particular, which is chapter 2, then you must know them. But when we move on to, let's say, chapter 3 and 4, well, most likely you will encounter these two guys, right? Gamma and normal won't be seen as much. All right. So what question can be asked about continuous random variable? Well, let's say, right? And so, okay, so random variables here, right, is one-dimensional. You can also have joint, right? Continuous joint random variable, okay? So, which is f sub xy of xy, right? Equals blah, 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 given in a range of, you know, domain, right? So this is also, right, something that should be covered in probability. So anyway, I mean, not much we can say here about the joint, except that you should know basic thing about the joint behavior of continuous random variable. So let's give you a quiz. This is quiz, I don't know, 7. So this is question number 36, right? In your textbook. Says a point is uniformly distributed within a disk of radius 1. All right. They say that means the density, the joint density, is C anywhere within the unit circle. And they say find the probability that the distance of the point from the origin is less than or equal to a number X. Sorry, this is inside, like that. All right, so first of all, do we know what C is? C should be 1 for pi, right? Because, you know, basically you have a unit circle, right? Radius 1. And the point, right, is equally likely anywhere in the circle. Therefore, right, the PDF is 1 over the area, right, which is pi. Anyway, so once we know that, then the probability that the distance, right, from the origin will be what? S equal to X will be what? Well, you see, right, in terms of the picture, what should it be? It should be within any kind of small circle, right, of radius X, right? Because that's the only way for it to have distance from the origin less than or equal to X. But because the distribution is uniform, then the probability will just be the ratio of the two areas. Right? This is only true for uniform distribution, right? So the answer here is going to be pi X squared, which is the area of the smaller circle, over the total area, which is pi, right? And so the final answer is X squared. Okay, any question? All right, last question. So this is sort of a very typical question in statistics, but it will show up here in this class as well. It's called the order stats, right? Order statistics. You have IID random variable with some PDF function. All right. And you, let's say, look at the max. and you want to find the PDF. Of the max. All right, how do we do that? All right. So with continuous random variable, unless we have a special scenario like this problem, a lot of times you proceed with the CDF function, which means you start with something like this. I mean, it depends, but right. So this is called a CDF, right? Cumulative distribution function. And so you try to figure out what this is, because the PDF will be the derivative, right, of the CDF. And so what is this? This is going to be the max less than or equal to x, right? But the max less than or equal to x is the same as individually all random variables less than or equal to x. But now because they're independent, that's going to be the product. But now because they're identical with the same density, that will be like that. All right. So that's the CDF of the max. But what are we after? We're after the PDF, right? So the PDF of the max will be the derivative, right, of this guy. Which will be n times this raised to the n minus 1 power. But we need to do the chain rule to differentiate inside respect to x. So multiply with like that. All right, any question? So, right, is this expression times that is this PDF of the max. Any question? All right. If not, then I'll see you on Wednesday. Okay.